Welcome everyone. So this is our 30th live stream geometry. So the IMO just happened this weekend, and it was a pretty hard IMO. So the first day, problems 2 and 3 were super hard, and problem 3 was geometry. So I'm hoping to do a video on that sometime. And also the IMO shortlist from the previous year was released. So that should give me some good problems for my channel. So Anmal just asked, are the IMO results out? Yes, they are. So I could tell you the website for that after. But today, in today's session, I'm going to go over the China Girls Math Olympiad. So we did that last time, but it has a lot of good problems, so I wanted to continue doing it. So with that, I am going to share my screen. All right, can everyone see it? All right. By the way, do any of you know of anyone else on the channel that participated in the IMO? I know Timo did. All right, so I'm going to start with this question. So we have an acute triangle ABC with AB greater than AC. D and E are the midpoints of AB and AC. So Irajan, are any of those of your friends on the Discord or on this channel? I think it would be cool, really cool if we had like a bunch of, very cool. Well, I'm glad that they do. Thanks for letting me know. All right, so D and E are the midpoints of AB and AC. And then we draw the circumcircle of AD. And we see where it intersects the circumcircle of BCD and BCD. So P and Q. All right, so this BCD, it intersects it at Q. And then the intersection point with BC intersects it at P, and we want to show that AP equals AQ. I'm going to make the diagram look a little bit better. Maybe something like that. That looks better. All right. So D and E are the midpoints, so DE is parallel to BC. I wonder if the problem is true for any D and E parallel to BC, but it asks about the midpoints. So maybe spiral similarities might be a good way to go. So we want to show AP is equal to AQ. So we could try congruent triangles. We could try spiral similarities. What's the best way to go here? So showing that AP, I invert about A. And what radius? Should I invert about yeah, I'm not sure what radius I should choose. Maybe any radius. Okay. So what would that do? So if I pick a circle, let's say, and I try to invert everything about it. Yeah, let's think a little bit through it before doing it. How would that help? So I guess we could also show that angle P. Oh, I think this has to be simpler. We could try to show angle PEA is equal to angle QDA. I think that might solve it really quickly. So angle PEA is equal to angle PBA, and angle QDA is equal to QCB. So we want to show PBC is QCB. Let me check that. But I think that might be a more efficient way. Yeah. So those are both 52.1 degrees. I'm going to draw in those segments. Okay, and PBC it's PBD plus DBC. And QCB is ACB minus Q minus ACQ. And ACB is AEB, and ABC is ADE. So I think that might help a little bit. BC, QD, and EQ concur. BC. Oh yeah, I was gonna say QE and wait, PD. What are the three that concur? That doesn't. Oh, QD and PE, maybe you meant. I think you might have meant that. Yeah. Okay. By the radical axis theorem, I'm guessing, right? Yeah. All right. But okay, so we want to show PBC is equal to QCB. I wonder if they concur. Yeah, they concur on the circle. So I think if we can show that, I think we're well on our way. Can I draw AF? Yes. But I feel like an AF, that might be tangent at A. Yeah. Looks like it. But it looks like yeah, so angle PBC then because angle PGQ would equal angle, oh, I don't think it equals angle A exactly. Let's see. But yeah, we want to show GBC as isosceles. That would solve it. Yeah, I feel like this problem has to be solved any second. I could try that, introduce the midpoint of BC. Let's think though, before we keep drawing new stuff. It feels like there has to be some way to finish this off. So yeah, I'm just thinking. Are these angles, let me check. Is this angle equal to this angle? No. Yeah, let's see if we can show BP and QC meet on this circle. Is that just an angle chase? Is PGQ is equal to PEQ? Okay, yeah, I think that might be an angle chase because we want to show this plus this is 180 minus PEQ. But PEQ, no, we haven't proven it yet. We haven't proven yet that G is on a circle. I think it should be an angle chase, but there would be some work to do. Oh, is it just Pascal's theorem? Because GP and AD is B, GQ and AD intersect at C, and PE and DQ meet at F. So yeah, by the converse of Pascal's, G has to lie on this circle. Okay. And then once we know that, is it obvious from there? Let's see. You have a solution with inversion. I feel like, so yeah, I've been wanting to use inversion on more of my problems, but I feel like, hold on just a sec. So, G and H are reflections over DE. Let's see. Yeah, it does look like it. Yeah, there's just too much structure here. Like, I feel like there has to be, I just want to see if there's like a simple solution to this, because I feel like there has to be. Yeah. If we can show GBC as isosceles, that solves the problem. Let me just think quickly if there's a way to do that. So, I think it can be done. So, we have angle GBC. It's DBC plus GBD. And GBD, DBC is ADE, and GBD is GDA minus PGD. So that would be GDE minus PGD. So we want to show GDE minus PGD is GED minus QGE. Let me think about this for a sec. So we want to show is GQ a diameter of this circle? I feel like it. I think it is. No. Let me write this out. So all right, let me, I'm just going to write out some stuff over here. Let me make the diagram a little nicer. Whoops. All right. So we have angle GBC. It's GBD plus DBC. Which is so GBD is GDA minus PGD. Then DBC is ADE. No, I'm sorry, this should be GDA right here. Which is angle GDE minus PGD. And then similarly, angle GCD is equal to, that would be like AED actually, let me just write it all out. So angle GCD is ACB minus ACG, which is angle AEB minus so ACG, that is AQG minus EAQ. And that simplifies to angle 1 sec. AED. AQCF looks cyclic. It's probably true. Yes. Let me finish this up. So what happened here? DPC. So GCB is ACB minus ACG, which is AED minus, I think I did this right? AED minus, so that's AED plus EAQ. Okay, so AQG is the same as AEG. So I'll just say that this is an AED minus AEG is GED. So this is angle GED plus angle EAQ. All right, so I think we're getting somewhere here. What's going on? Oh, whoops. Okay, so we want to show these are equal. So GDE is equal to GED plus E. Okay, so GED is arc GD plus this arc Is this right here? So GE. Yeah, this just feels so random.
What is the other point on BC?
Oh, this point?
Yeah. Do we know F is tangent to the circle?
I think it, but we don't know it yet. We can prove using power of a point that, okay. I feel like we're probably making it more complicated than it has to be, but oh well. Let me check. So Feng said he had a solution using inversion. Feng, can you type that up in the chat?
Okay.
All right, thanks.
So I will use inversion. Inversion AD plus AC.
Okay. So you're inverting about A, right?
Yeah. The inversion A.
Okay.
A is is the power. Yeah, and we claim that AD plus AC equal to AA plus AB.
AD plus AC.
Yeah.
Is equal to what? I'm sorry.
Equal to AE plus AB.
Ah, okay.
Yeah.
After the inversion, I'm guessing, right?
Oh, after the inversion. Okay. Now just let me type it.
Yeah, type it in the chat. That might make it a little easier. Let me check this again. After inversion, B is the midpoint of AD. Okay, so if I pick a circle with any radius, and then I invert, oops. So yeah, B prime. I guess it's good to call, yeah, just call things like prime. Okay. So yeah, B prime is the midpoint of AD prime, right? Ah, so it's like a root BC inversion. Okay, so you're saying B goes to point E, and C goes to point D. Let's think about that. And that would be because AE, so yeah, because you're saying AE times AB is AD times AC, so we can invert. Yeah, so the radius would be the square root of AB times AE would be root AB times AE. So AB times AE is equal to AD times AC. And so the square root of that, we can invert about a circle with that radius. So B goes to E and C goes to B. I agree with that. So the circumcircle of BCD goes to the circumcircle of BEC. Okay. I agree with that. And then we can say the same thing with the other circle. And then how does that end up solving it? So yeah, the circumcircle BEC goes to DEB. I agree with that. And then how does that end up showing that AP is equal to AQ? So I guess P would go to, I guess.
Yeah.
Okay.
After that, we let the circumcircle of DEC intersect BC at P1. So P will transform to P1.
P will transform to P1.
Yes, because P is the intersect of B, the circumcircle of BCE with ADE. But after the inversion, the circumcircle of ADE transfer to BC.
The line BC.
Yeah, the line BC. Yeah.
So it would be where BC intersects the circumcircle of, let's see, so BEC goes to
DEC. Yeah, as P1.
Okay, so P1 would be, hold on just a sec. So BEC goes to DEB. So we drew, let me draw DEB.
Yep.
And so it would be this point right here, right?
Yes. Then we have to prove that AP1 is equal to AQ1.
Okay. So that's P prime. So we'll call that P prime. And then we could also draw Q prime.
Yes, Q prime and P prime.
So that was BED and then CED. It would be, so this would be Q prime right here.
Yes.
And then we want to show P prime equals Q prime.
Yeah.
It looks like these are both isosceles trapezoids, right? Maybe that's, yeah,
yes.
They have to be because those are parallel and they're cyclic. So
yes.
How do we show that AP prime equals AQ prime?
Okay, so we will exchange the angle. You have to draw the AQ prime and AP prime. Is easy to look.
Okay.
Okay. So we claim that D, Q prime and B is equal to E, C, and P prime.
Okay, and that's true because this is an isosceles trapezoid, right?
Okay. And A, P prime, Q prime is equal to C, P prime, E prime, E, C, P prime, E plus E, P prime, A.
Okay.
Yeah, and A, Q prime, C is equal to B, Q prime, D plus D, Q prime, A. So we have to prove that D, Q prime, A is equal to A, P prime, E. Oh, no. D, A, Q is equal to A, P prime, E.
Okay.
Okay.
All right, I'm gonna write this out. So I kind of like that. So yeah, this is like the first. I'm gonna delete some stuff, but this is like the first proof I've done on my channel that's like a root BC inversion.
Okay.
But thanks for bringing it up. So I'm gonna delete just a couple things.
Yeah, I will write it down. Easy to look then say.
Okay. Okay, so we have AD times AC equal to half of AB times AC which is equal to AE times AB. So then we can consider an inversion about a circle centered at A. With radius followed by a reflection about the angle bisector of A. All right. So D D and C are swapped, and then B and E are swapped. Yeah, we did overkill this. I'm just really curious about this. So the circumcircle of ADE goes to line BC. And the circumcircle of BCE is sent to BC. So yeah, so DE or FEC. And BCD is sent to EFB. Okay. So therefore, P is sent to, let P be sent to P prime and Q be sent to Q prime. So let's see. So where's P prime? I think I accidentally deleted it, but it's so it would be BC intersect there is no point F. This should be DEC and DEB. So that would be BC intersect DEB. And DEB and DEC. So if we could show A prime equals Q prime, then we would solve it. I'm sorry, AP prime equals AQ prime. All right. That's a real, and then, okay, so Feng says we claim angle ABQ prime equals E. ABQ prime is EQ prime C. What does that phrase mean? Ben, dem, mem, oldem.
You know, it's kind of easy. Yeah, we just have to prove two angles is equal to each other. Yeah.
Okay. So.
And yeah.
Okay. So I'm gonna write. So ADQ prime is equal to P prime EA. So yeah, we have two isosceles trapezoids, right? DE prime C is an isosceles trapezoid. DB P prime E is an isosceles trapezoid. So yeah, I wonder if there's like a simpler way to show. Hold on just a second. AD equals BD. Okay, so I'm going to type out what you put. Oops, sorry. All right, so then we have this. So ADQ prime is congruent to P prime EA. All right. And so then that means AP is equal to, that means AP prime is equal to AQ prime implies AP equals AQ. Let me think about this for just a sec. So we have AD equals BD is equal to EP prime, because that's an isosceles trapezoid. And then we also have AE is equal to BQ prime. All right, I think this looks good. I'll just add I like this proof. Thanks a lot for sharing it, Fwang.
Okay.
It also suffices to show GA equals GP. Yeah, so we actually didn't need point G for this proof, although I'm sure there were ways to do it. So yeah, if we could show GA AG is equal to AE. Oh, no. Oh, GA is equal to GD. GA is not equal to GD. But yeah, I'm just going to erase G from the figure. Oh, that's all right. Just because it wasn't involved in the proof. All right, so I'm going to move on to the next problem. All right. So let O be the intersection of the diagonals of ABCD. All right. The circumcircles of OAB. Whoops. And OBC meet at O and M. So M is the other intersection point. OM meets the circumcircles of OAB and OCD at T and S. And we want to show that M is the midpoint of TS. That's interesting. So this is T. So I guess that means M has the same power with respect to both those circles, right? So maybe this will be an easy problem. M is the center of the spiral similarity. Yeah, because it's the intersection of so many different circles. It has to be, whoops, sorry about that. So yeah, spiral similarity takes MBC to MAB. So yeah, MBC and MAB are similar. And we want to show M has the same power with respect to these two circles, right? So how would we do that? Maybe we could use Casey's theorem. So let me draw the centers of all four circles. There we go. MBD is similar to MCA. Yeah. So MBD is similar to MCA and MBC is similar to MAD. So we have a lot of similar triangles here. Maybe invert at O. That would be cool. Another inversion solution. Hold on just a second though. I feel like we just want to show M has the same power with respect to those two circles, right? So I feel like there should be, does MG equal, whoops, sorry.
Can you draw the perpendicular from M to TS?
From M to TS, draw the perpendicular? Like
Maybe
that.
this is concurrent with PB and TS. Can you check it?
With A, B, and CD?
No, PB and TS. TB.
Oh, TB and CS, I'm guessing. No, but it's close. So yeah, if I move it around.
We can check AB and DC.
We can change A, B, and BC.
AB and DC, we can check if they are concurrent. I said DC, but it's not, I think.
Oh, sorry. Maybe invert at O. Yeah, I think inverting at O might work. But I mean, yeah, I feel like there has to be a way to show that trivial by similar triangles. So Ira, John, do you have a solution? One second, guys. I'll be right back. All right. Okay.
Can you let DA cut the circumcircles of COD and BOA?
Can I let DA cut it? These two points? Sorry.
Yeah.
There we go. Almost looks like OI is equal to OJ. Is that true? I think it is. No. Just looked like it.
AM is parallel to JS.
AM is parallel to JS. Interesting.
You can do the same with I. This can work.
That's interesting. PMD similar to ACD. Let's check. Looks like it. Let me check one more angle. Yeah, they're similar. Does that solve it? Let's see. Yeah, because, okay, so one of the angles has to be equal, and then can we show by an angle chase that the other has to be equal? Yeah, so I wonder if that just solves it. So TMB is similar to ABC, and SCM would be similar to BBC. I think that, yeah, okay, yeah, okay. So I think there's a really simple solution here. Okay, so yeah, let me delete a couple things, but I think there's an easy solution. Let me make some room here. So first I'm going to show triangle TBM is similar to ABC. Or maybe it might be easier to show TBA is similar to MBC.
Mr. Michael, triangle ACD is similar to MSD.
Mm-hmm. Yeah.
Yes.
That's like the same idea. Yeah. So we have actually 4 similar triangles. Did you say so? MAD is similar to TSD, was it? Or I'm sorry, what was the or
CAD is similar
MSD,
to
right? Yeah.
SMB. Yeah.
All right. So yeah, it's so yeah, Irajan in the chat had the similar idea. So I'm gonna write this out. So first I'm gonna show TBM is similar to MBC. So we have hold on just a second. So we have angle MBC is angle MOC, which is angle TOA, which is angle TBA. All right. And then by the same argument, we have angle angle MCB is equal to angle BOT, which is equal to angle BAT. So MCB is similar to BAT. Hold on a sec. Or BTM is similar to BAC. So BTM is similar to BAC. We have angle, actually, angle BTO is equal to angle BAC. Let me rewrite this. All right. And we also have angle TBM. TBA plus ABO. Or I'll just say angle TBA. Angle TBA is TOA. Hold on just a sec. So the last one implies that angle TBM is equal to angle ABC. And so that means that BTM is similar to BAC. And then similarly, CSM is similar to DCB. And those 2 similarities, I think, should solve it because actually, let me think, is it that obvious? Because TM over BC, let me read the chat. So And then we also have yeah, BMC is similar to ATB. So ABC is similar to TBM. BCD is similar to SCM, and MDB is similar to MAC. MDB is similar to MAC. So by spiral similarity at M, this is true. And then if we combine those three, then you're saying it gives a result, because, so let me write it all out, but we have PM, so we have PM over BM is equal to AC over BC. And then we also have SM over CM is equal to DCB. SM over CM is BD over BC. And then we also have, by the third spiral similarity, we have BM over DM, or BM over BD is CM over AC. So combining them, TM is equal to SM. Very nice. That's an awesome solution. All right. So M is the midpoint of ST. All right. Thanks everyone for your help on this. That was a nice solution. So I'm going to move on to the next one. So we have a trapezoid. Oh, this was an interesting one. I just looked at it really quickly, but I'm going to draw like a tall trapezoid. So, whoops, hold on just a second. Maybe even taller, just to make the problem easier. So we have like a trapezoid. And BA, AB, and BC. So we draw a circle tangent to these three and another one tangent to these three. So I'll do it this way. Whoops. So we draw this circle, and then we draw a similar circle down here. Right? I'm going to hide these extra lines. And so this one has center, let's call this one O1. And this one is O2. And this is P. and this is Q, and it's saying to prove that AC, BD, and PQ are, oh, this should be concurrent. I'm sorry. Concurrent. There we go. So, and in the contest, they actually drew the figure for you. In fact, they did that for a couple problems, which I kind of like. So yeah, it's kind of an interesting thing that these three lines are concurrent. I think we should probably extend AD and BC. I think that might be helpful. So, because then we'd have like an in circle and an X circle. So let me do that, and then I'll read the chat. AP over PB is equal to CQ over QD. Oh, you're asking if that's true. It could be. I'm not sure. I think, okay, you're saying that would solve it. Is it true by in-center and X-center stuff? So P is the, yeah, I think it's true by homophoties. So yeah, I guess this is an easy problem. So, but why does that solve it? Is that just, I think it's probably trivial. Yeah, because, yeah, okay. So that solves it. So I'm gonna let AC intersect BD at X. And then P and Q are corresponding points in those two similar triangles. So yeah, okay. So yeah, I don't want to make it look like O1 lies on that diagonal. So I'm just playing around with things a little bit. Just bear with me for a second. Yeah, it looks like Q1 lies on the diagonal, but there we go. That's probably a little better. So basically, I'm going to draw the in circle of EAB. Let me just make this slightly straighter because that's like, there we go. But yeah, that pretty much solves it. So all right, so X is that intersection point. Let AD intersect BC at E. And then draw the in circle of AB. So and then let it be tangent to AB at F. By a well-known fact, AF is equal to F is equal to BF. So by a well-known fact, so see my video on the IM lemma. AF is equal to PB. And then also by a homophily at E, EF and Q are collinear. So and so EQ over QC is equal to AF over FB, which is equal to BP over PA. And so so that we have triangle AXB and CXD are similar. And with P corresponding to Q, and then that means that PX and Q are collinear. So that means that AC, BD, and PQ are concurrent. All right, so I'm going to move on to the next problem. That was a quick one. See what you guys put in the chat. You only need Thales' theorem. So, yeah, I guess you don't even need O1 and O2, right? You don't, or I could hide. Whoops. Sorry. That makes it look nicer. But you said it only needs Thales' theorem, so it doesn't even need. Does it need stuff about N centers and X centers? I don't know. But yeah, in any case, it's a short proof. I'm going to move on to this one. All right, so we have a right triangle inscribed in a circle. So angle A, we want angle A to be 90. So B, let's do it like this. So that's B, this is C. This point we're going to rename it to be A. And the center of the circle, we could call it O for now, I guess. Oh no, because O is used later. Let's call it P. E lies on the interior of arc BC, not containing A. So we want EA to be greater than EC. And F lies on EC, and we want angle EAC to equal angle CAF. Okay, so what I'm going to do, I'm going to reflect this about that. So this will be point F. And BF meets the circle again at D. This is point D. And we want O to be the circumcenter of BEF. Okay, so I'm going to draw that circle. So O is the center of B. And we want to show that AC and O are collinear. All right, so hold on just a second. Whoops. What else did I hide? Oh, EC and F. I want to draw that segment. Oh, AF. Yeah, I want to draw AF and I want to draw this. So AC is an angle bisector. And I think that's like really all that we need, right? want to show AEOF is cyclic. Yeah, because O lies on the perpendicular bisector VF. Yeah, so we want to show AEOF is cyclic. Sorry, I just heard someone chat on Discord. Let me check. Give me just a second. You know what? I'll go check it later. So we want to show AC and O are collinear. Oh, hey, Raghav. Thanks for joining. All right. Oops, sorry. All right. I think it might be an angle chase to show that it's cyclic. Let's see. The in-center of AEF. So it looks like it's like the intersection of AC with that arc. Maybe that's like an angle chase or something. So if we let AC meet the circle at point G, can we show that G is the in-center? So angle GEF would be angle GED.
Yeah, FDC is 90 degree and CDE is half of A. So it's done. They're cyclic.
So you said FDC is 90 degrees?
Yeah.
And then, so FDC is 90, and what did you say is half?
CDE.
CDE.
Yeah, because it's angle bisect.
So CDE is CAE, which is CAF.
Yeah, so FDE is 90 plus half of A, and FGE is 90 plus half of A.
And so based on that, we can calculate angle FOE. So then we can show FOEA is cyclic, and then that solves it. So yeah, we don't even need the in-center stuff, do we? Yeah, I don't even think we need the stuff about the in-center. So I don't even think we need point G, really. I think we just need, yeah. So let me start writing it up. But yeah, I think that is easy enough. I think hopefully the last two problems will be harder. I think they will be, but if not, we can always get more problems. So angle BDC is 90 implies angle FDC is 90. All right. And angle EDC is equal to angle EAC is equal to angle FAC. And so angle EDF, or or I'll just say is EAC is half of angle EAF. And so angle EDF is half of angle EAF plus 90. And that means angle EOF is twice. So I'll write it like this. So we have angle EOF is twice 180 minus angle EDF, which would be 180 minus angle EAF. So that means that AEOF is cyclic. And then from there, we're pretty much done because since O lies on the perpendicular bisector VF, so, or I'll just say EO equals EF, or EO or OE is equal to OF. That means that AO bisects angle EAF. And that means that AC and O are collinear. And that solves the problem. Right. All right. That was a fast one. So let's try the next one. Okay. This one looked kind of interesting. So we have two